Next, a designee for Bill Boyle, who is the office director of NE81, which is a spent fuel and waste science and technology organization. And I will turn the time over to John Orchard, who's representing Bill today. Go ahead, John.
Well, good morning, Drew. I guess it's my name's John Orchard. Let me see, where did my slides go? I guess the next slide, please. Yeah, I'm with the NE8, the Spent Fuel and Waste Disposition Directorate. I'm in the Office of Spent Fuel and Waste Science and Technology, NE81. We also have the Integrated Waste Management Office, NE82, which will be presented shortly. I have presented draft mission statements, which are unofficial at this time, but they give you an idea of what we do. Overall, NE8, spent fuel and waste disposition, is the intention is to protect people and the environment now and in the future by establishing an integrated system for storage, transportation, and disposal of the nation's spent nuclear fuel and high-level radioactive waste. NE81, Spent Fuel and Waste Science and Technology, is to provide confidence in the safe long-term management of the nation's spent nuclear fuel and high-level radioactive waste by reducing uncertainty and advancing technology for extended storage, transportation, and geologic disposal. NE82 is integrated waste management, and that'll be presented by the next presenter. Next slide, please. Within NE81, we have two main research areas. The first is disposal research, and the second is storage and transportation. Within disposal research, we have several areas of focus. First is repository geology, which involves investigating argillite, crystalline, and salt as potential host rocks. The second is engineered barrier systems, which is studying the geochemical and mineralogical alterations that occur at elevated temperatures and the effect on interactions between the buffer materials and the waste package. The third is geologic disposal safety assessment, which is developing the features, events, and processes, which we call FEPS. Processes, the processes include the waste form and EBS evolution model, flow and transport model, and the biosphere model. And their direct disposal of dual purpose canisters, which are the existing method of long-term storage of the fuel, is to investigate criticality mitigation by using ceramic or cementitious fillers and performing criticality consequence analysis. In inventory and waste form characterization and performance, we are performing fuel matrix degradation modeling and testing. We're conducting isotope measurements on BWR and PWR fuels to more accurately estimate criticality burn-up credit for DPC, for loaded DPCs. And advanced reactor, spent nuclear fuel and high-level radioactive waste streams and waste forms. We're developing the FEPS for the GDSA, and we're developing a gap analysis for the storage and transportation safety analysis. Next slide, please. The second area that we are researching in spent fuel waste storage and our science and technology is we're looking at high burn-up fuel field test and sibling pin tests. We have a full-size fuel canister, which we've loaded with high burn-up fuel, and we're performing field tests on that. And in the meantime, we're testing examples or sibling specimens of the fuel rods that are in the test canister. So, and in the process, we're collecting temperature data from the field test canister. We're obtaining data and developing a gap analysis of the BWR, IFBA, ATF, and higher burn-up fuel, PWR fuels, and their cladding. And we're testing an analysis of the sibling pins. We're researching thermal profiles by testing an analysis of the canister and bare fuel storage systems in both the horizontal and vertical orientations during drying, storage, handling, and transportation of the canisters with the fuel in them. We're looking at stress profiles. Specifically, we're running a shaker table test on a full-size canister loaded with surrogate fuel and dummy fuel, and we're doing testing and analysis of the stresses and strains on the fuel bundles and the fuel assemblies. We're also studying the previously conducted 30-centimeter drop test analysis for their effects on pinch loads on the fuel cladding. And then we're looking at welded atmospheric corrosion, looking at chlorine-induced stress corrosion cracking, modeling, mitigation, and repair. We're performing a full-scale chloride dust canister deposition and deliquescence demonstration. Let's see, I think we have another slide. Yes. We're doing research on the drying process. Particularly, we're testing and analyzing lab scale, bench scale, and full scale canisters to develop simulation, sampling, and analysis techniques to quantify residual water as a function of the drying parameters and performing consequence analysis. Well, one of the concerns is that during the drying process there's residual water, and we're trying to determine how much. We're looking at canister failure consequences. If we have a through-wall crack, we're performing numerical and empirical models to study the crack size and particle size distribution, particle and aerosol flow through microchannels, and aerosol release and depletion rates. And then we're also studying canister internal environmental modeling by developing non-intrusive sensors and developing power supply and signal transmission technologies for monitoring the internal temperature, pressure, and the gas species and concentrations. Looking at the helium gas concentration in the which is the inerting gas in the canister. We're also looking at decay byproducts such as xenon and krypton that could be leaking through ruptured fuel cladding. Those are the main areas of our research for spent fuel waste storage and science and technology. That's my presentation. Thank you.